So today we're going to get into these rules and properties of logarithms, how we can apply logarithms to expressions, how do we simplify logarithmic expressions, all this good stuff. But before we do so, let's talk about domains of logs. So we ended yesterday with a function on the IC, and we had log base 7 of x squared minus 16. Before we do that, let's do one that's slightly different. It's a bit easier, I think, at least in terms of just the procedures. Let's say we've got x minus 5 over, say, negative 1 plus log base 2 of x plus 7. So we'll start off with g of x. The reason why I wanted to do with this one, because everything's linear. There's no squared terms. We do have this rational expression, though. And so what are our rules for domain? We cannot divide by 0. Cannot take an even root of a negative. Those are the two we've been using so far. And in particular, the second one, it's going to be very similar to how we deal with logarithms. And notice I did change it a little bit. We've been saying square root, but it is even roots, right? Any square root, fourth root, sixth root, any even root, we cannot have a negative number underneath that square root or that root. And now our third one we're going to add is that the inside of a log must be positive. And by positive, I mean strictly greater than 0. So we cannot be equal to 0. And so with the function we have, rules 1 and 3 are going to play a part. We're going to start with rule 3 because the innermost function is this logarithm. I always like to work with the inside out. And if we were to write this as a sequence of like nested functions of function compositions, we could write this log as the inside composition for this entire function. So what appears? We just have log base 2, and now inside of the log is x plus 7. So since that expression appears, we take this expression. So inside of a log must be positive. And if we have log base 2 of x plus 7, we can translate that, this third statement, as the x plus 7 has to be greater than 0. And solving, we simply get x is greater than negative 7. So that's our first restriction on our domain. We have to have our x values bigger than negative 7. Most of you guys kind of saw this yesterday on one of the log functions, I think number 2, when we took a log function and shifted it. Remember, the domain of a regular log function should be 0 to infinity. And what are we doing with this function? We're shifting it to the left 7. So from 0 to infinity, that domain then shifts left as well to negative 7 to infinity. But of course, we've got other things going on in this function. So rule number 1 says we cannot divide by 0. So let's write, that's rule number 3. Rule number 1, if we cannot divide by 0, the way we would write that mathematically means that the denominator, negative 1 plus log base 2, of x plus 7 cannot be, is not equal to 0. And I treat these non-equals, treat them just like equal signs, and solve it like we would. Now, we haven't quite solved something like this. So what we want to do is first isolate the logarithm. So this says that log base 2 of x plus 7 is not equal to 1. And now what we want to do is undo this logarithmic process. So we'll see some general rules here shortly once we get into our log rules, but we can apply the rewriting methods we were doing on Monday in terms of rewriting a logarithmic statement as an exponential statement. So what does this statement say? If log base 2 of x plus 7 is not equal to 1, we raise 2 as our base to the 1 is not equal to x plus 7. And now solving, I subtract 7, and we will get x is not equal to negative 5. These are our two domain restrictions. X is bigger than negative 7, but x is not equal to negative 5. So you could write that in set notation or in interval notation if you'd like. Our domain is now minus 7 up to minus 5, and then minus 5 to infinity. So that's our domain for g of x. Let's go back to f of x. Our domain here is going to be a little bit more complicated with the expressions that are involved because we're going to have a polynomial inequality. And we've only seen this a couple of times. Oops. That's just our function. And so we were going to use rule 1, again, inside of a log must be positive. As you notice with the last one, it doesn't mean x has to be positive. It's that the inside of the log, the resulting expression, after I evaluate that x, has to be positive, right? Our domain in the last guy, we had negative numbers. X could be negative 2. X could be negative 6. Those are fine to plug in because when I add 7, the result will be positive. And so now we have to think of what to do with a square. So inside of a log must be positive. Mathematically says the inside of the log, x squared minus 16, has to be greater than 0. That gives us a nice mathematical sentence. And how do we solve something like this? So recall back a couple weeks when we did rational functions. You don't want to just add the 16 and take a square root. It's not entirely wrong, but the problem is when you solve things like that, when you take a square root, you have to apply a plus and minus. And you got to be careful about what that plus and minus means with these inequalities in terms of especially minuses. If you remember with absolute values, whenever we have these minuses come up in absolute value inequalities, it flips the inequality. So the best way to do these, I would say, is to factor. And now what we're going to do is a number line. So we've done this with rational functions. You'll do this a lot in calculus and doing these number line tests, determining when your functions are increasing and decreasing. For now, what we want to ask is, well, this inside of a log we can consider as a function in and of itself, x squared minus 16. It's just a parabola. And what this statement is asking is, where is this parabola positive? Where is it above the y-axis? So what we're going to do is we're going to plot a number line. And on this number line, we're going to plot our zeros, because that is ultimately what we want to compare it to. If I want the regions that are greater than 0, we want to know, well, first, where is it equal to 0? And then what we're going to do is pick test points. And we are going to evaluate those points and determine, am I positive or negative in that region? So for example, when x equals 0, we will get -4 times 4. And you don't actually have to multiply these out. This is another one of these situations. Because we're comparing to 0, I just want to determine positive or negative. And sometimes the numbers can be kind of hard to multiply out, but that's not the big thing. The big thing is that I'm multiplying two quantities together. The first one is negative, and the second one is positive. And when I multiply a negative times a positive, overall, we will get a negative. So within this region, from -4 to 4, our function is going to be negative. Let's pick our other test points, so maybe 5 and -5. And when we check x equals 5, we will get a positive times a positive. And so we'll overall be a positive in that region. X equals -5, we will get -9, so negative times -1, again a negative. A negative times a negative overall gives me a positive. And so when you're done with your number line test, what you want to do is then go back and see, what am I looking for? For our purposes, we are always looking for greater than 0. And because we are greater than 0, we want the positive. We want the pluses. So we'll have -infinity up to -4 union 4 to infinity will be the domain. The other thing you can think about is this x squared minus 16 is just a function. What we kind of summarized in this number line test was, where is the function positive? Where are the values of the function? Where are the y values positive? Where are the y values above the x-axis? And so this is a parabola. And what you could do is draw it, or you could argue in pre-calc ways by saying that x squared minus 16 is a parabola with zeros of 4 and -4. And because the lead coefficient is positive, we know that the parabola should open upward. In other words, if it's opening upward and we are asking, where is this function positive, it has to be from -4 or negative infinity up to -4 and then 4 to infinity. We know that the ends will be going off to positive infinity when the x values are either really small or really large. And so this is exactly what we summarized here. The graph is above the y-axis, below the y-axis, and then above the y-axis. Any questions on that? Okay, let's talk about our log rules and simplifying logarithmic expressions. So first one is evaluating basic logs. I want everyone to start putting these in your brain that will be useful for the rest of your mathematical careers. Log base b of 1 is 0 for no matter what base. So in calc, you'll use a lot of natural logs. Natural log of 1 is equal to 0. Log base 10 of 1 is 0. Log base b of b is 1. This means natural log of e is 1. Log base 10 of 10 is 1. Sorry, you guys were saying blurry? And so our last one, log base b of 0 is undefined. Better term will be minus infinity when we actually compute the limits. And as the limits of x, as x gets closer and closer to 0, logs will decrease to negative infinity. And so our other properties, we will have the fact that exponentials and logarithms are inverses to each other. So if I have one function that's b to the x and the other function that is log base b of x, then f composed g of x, which is going to be b to the log base b of x, equals x. This is the property of inverse functions. Namely, these processes of exponentiation and logarithmic applications are inverses to each other. They undo each other. So if I have a number x that I first apply a logarithm to that number and then exponentiate that, the exponential and logarithm undo each other, and I end up with the number that we started with, and vice versa. G of f of x is equal to log base b of b to the x. In other words, if I exponentiate a number first and then apply a logarithm of the same base, it will undo that exponentiation, and I end up with the number that we started. And then our last set of properties are going to involve sums to addition and, or excuse me, multiplication to addition and division to subtraction. So log of a times b, a and b can be any expressions, is going to be, sorry, log base b, any base, log base b of a plus log base b of b. So multiplication inside turns into sum outside of the logs. Likewise, if we have division, this is going to turn into subtraction. Again, division inside. Turns into subtraction outside. And our last one in that vein is exponentiation. So if I have exponentiation inside of a log, this is going to equal multiplication outside. And then our last rule is our change of base formula. So if I have log base b of x, and we don't like that base for some reason, maybe because we want to plug in a number to a calculator, and some calculators, most calculators, only have natural log and log base 10. So what you want to do is change, say, a log base 2 to a log base 10, so you can compute it and get a numerical approximation. How do you do that? You take the original expression, you change it to whatever the base you want it. So log base c of x. Then you just have to adjust it by dividing by a constant. And that constant is going to be, again, a log base c, because that's the one we want to change to, of whatever the old base is. All right, everyone got all those written down? Okay, so let's do some examples. Keep that page handy. And so let's say we want to simplify. And the first expression is 5 to the log base 5 of x plus 1. So what do we have? We have some expression, x plus 1. We are then applying a log base 5, and then we are taking that and exponentiating it. And we're going to use our inverse properties that exponentiation and logarithms are inverse of each other. So this 5 raised to a log base 5 essentially cancel, so to speak, and we are left with the argument inside the log. So this just simplifies to x plus 1. Our next example, we want to simplify log base 1/2 of 2 to the 9x. There's a couple different ways we could get this started. We want to, again, take advantage of this fact that logs and exponents are inverse to each other. Our problem is that we need the bases the same. Base of the log and the base of the exponential have to be the same in order to apply this inverse property. So 1/2 and 2 aren't the same base, but we can make it the same base doing some algebraic tricks, because 1/2 is simply 2 to the minus 1, and vice versa. So what we can do is write this as log base 1/2. 2 is 1/2 to the minus 1. So we can write this as 1/2 to the negative 9x, where 2 to the minus 1 is 1/2, and then we'll have that minus 1 times 9x, gives me that negative 9x in the exponent. And now we can use this inverse property. Log base 1/2 is going to undo the exponential to the 1/2, and we are simply left with whatever the argument is, with negative 9x. The other thing we can do is, if we wanted to do a couple steps, is since I have an exponentiation inside of a log, that is multiplication outside of the log, and now we can use the rule that log of base 1/2 of 1/2 is just 1. So 1 times negative 9x gives me negative 9x. So this one says simplify to an integer. It might just say simplify, but your answer cannot be an integer. These are problems that we like to see a bit on tests and quizzes to challenge your guys' basic skills of logarithms and using these multiplication to sum and product or difference to quotient properties. We got log base 6 of 45 plus log base 6 of 28 minus log base 6 of 35. And we want to simplify this. And we should get an integer. So how do we do a problem like this? The way I like to do it is to combine everything as one log. There's going to be other problems that you'll see that might say write as a single logarithm. Write this expression as a single logarithm. That's the way I like to start. And so we are going to use these properties, primarily properties, these first two here, that a sum outside is going to be multiplication inside. So we're actually going to be going this direction with these sums and differences that we have outside of the logs to write things as products and quotients inside of the log. So we can start with the first two. I've got log base 6 on all of these. That's a key point. We have to have the same base of the log in order to apply these properties. So the first two are going to simplify. Log base 6, we will have 45 times 28. And as a tip with these types of problems, especially if the numbers are, even 2 digits, you don't want to multiply 45 times 28. Don't do that. It's a waste of time, waste of arithmetic, waste of brain power. I would recommend with all of these, keep it as just written 45 times 28. And then this next step, let's go ahead and combine these last two logs. We will have log base 6, 45 times 28 in the numerator. And then since we have subtraction, we'll have division inside the log by that argument, 35. Keep it like that. Don't multiply things out. Because the easiest way to simplify this now is actually to factor those numbers more and look for factors to cancel, look for factors to divide. So we will have 9 times 5 is 45. 28 is 4 times 7. And 35 is 5 times 7. And then now we can divide those 5s, divide those 7s. And so we are simply left with log base 6 of 9 times 5. 9 times 4. Once you've simplified all the factors, I would say multiply that out. 9 times 4 is easy enough to do. We've got log base 6 of 36. And if we wanted to do this in steps, now we've got log base 6 of 6 squared. And the base of the log matches that base of the exponent. So this is just going to be 2. Any questions on that guy? Okay. So we'll see a few more. Other than combining things into one log, the other thing we might want to do is to expand expressions. We've got log of x cubed over 2 square root of y. And when we say expand, what we want to do is use the power rule, the product to sum, the quotient to difference rule, and write everything as essentially linear factors of logarithms. So the first rule we're going to take advantage of is this quotient. So I'll have a log of x cubed minus log of 2 squared of y. And now let's keep the log of x cubed. We'll deal with the exponent in the next step because we still have one more product in the second logarithmic expression. Be careful with this one though, since it's a subtraction, we are subtracting off this whole term. So we'll write it as minus quantity log, and it's a 2 times y, square root of y. So it'll be a 2 plus log square root of y. And when we distribute that minus, we'll get a negative log 2 and minus log of square root of y. Notice that in the original expression, anything that appears in the denominator has a minus out in front of it. And our last step now is to deal with the exponents. So we can use this exponentiation to product rule. So log of x cubed will be written as 3 log of x. Log of 2 is as simplified as we can get it. And we also want to remember that square roots are fractional exponents. So square root of y is y to the 1/2. And so when I apply a log to that, I can bring down the exponent as multiplication out front.
I have a question. Why did it change from plus log square root of y to minus?
We have a minus sign here. So we needed to distribute this negative sign to both of those terms. We are subtracting off this whole expression. You can think of this as minus 1 times log of 2 squared of y. So even though log of 2 times square root of y is log 2 plus log squared of y, since we are subtracting off that whole expression, both of those will end up being negative once we distribute that. Okay. So we can do some other simplifications. Let's do some simplifications with natural logs and maybe apply our change of base. Let's say we've got change to base 10. And we've got log base 2 of 10. To apply our change of base formula, remember we want base 10 starting with base 2. So we will have a base 10 is what we want to end up with. Keep the same argument. So we'll have log base 10 of 10. And then we got to divide by log base 10 of the old base. And now simplifying that, we can at least simplify log base 10 of 10. And so that will give me 1. Log base 10 of 2 is just a number. If we have numbers inside of logarithms, it's just a number, like pi, e, square root of 5. That is what it is. But that one we can at least type into a calculator, since the calculators have log base 10. Let's simplify natural log of natural log of e to the e to the 9. So with these, I would recommend, I always like to work inside out. So on this innermost log, this whole expression of e to the 9th is in the numerator, or in the exponent. And using these exponential the product properties, this means I can bring down that e to the 9th that's in the exponent, write it as multiplication outside the inside natural log. Natural log of e is just 1. So now we are just left with natural log of e to the 9th. And again, I can bring out that 9. And again, natural log of e is just 1. Any questions on any of those?